Good morning, I'm Bob Finch with Select Spectrum. Very pleased to have you join for this session on dual frequency 4G and 5G networks. Pretty exciting that we can actually, a few years ago we were struggling to find frequencies. We now actually have some available, we have technology available, and we have examples in the case of Idaho Power that at least has dual frequency. I don't know that Sean is 4G, 5G yet, but maybe in his future. The plan here is, I'll do a very brief introduction, then Sean will come up and speak about what Idaho Power has done. By the way, Sean is a principal engineer for Idaho Power, BSEE from the University of Idaho, and very active in UTC. For those, probably most of you know him. Then I'll speak briefly. I'm president and founder of Select Spectrum. We're a brokerage for licensed spectrum. I'm a former engineer, and I'll tell you a little bit more about my background as it relates to the presentation. And then our true technologist in the development side and vendor side, John Baldwin from 4RF. He's actually a founding director for 4RF. He was the leader of the development of the Aprisa line, and formerly had significant experience in other telecom manufacturing companies as well. So we'll do 15 minutes each. We're going to ask you to hold questions for the end. There is quite a lot of content here, but please do think about them and be ready to shoot when we come to the end. And with that, I'll bring up Sean.
Thank you all. Can you hear me all right? All right. It's really great to see everyone again. I've missed this. I can't say I've totally missed presenting. However, I don't mind it too much, but I really like the engagement that we have when we're together. It's a little bit more challenging over the internet, but I mean, it works as well, but it's really great to see everyone here. So thank you for coming. And thank you for that introduction, Bob. And thanks for inviting me to the panel, both John and Bob, so thank you. So I'm going to lay the background of where Idaho Power's been at in this arena, and like Bob alluded to, we're not using 4G or 5G currently. However, where we're at has some directions that point in that direction, not to be redundant, but it definitely points in that sort of direction given the current state of affairs in distribution, automation, its new name grid mod, and in general power system and employees of electric utilities and their needs. So just not going to spend a lot of time here. Idaho Power, we're in southern Idaho and eastern Oregon, really, 24,000 square miles of service territory, 17 hydro plants. We're pretty hydro heavy, and I don't know, 300 and almost 400 substations. We've got some clean energy goals that are coming pretty soon. I think by 2045 we're looking at 100% clean energy. A lot of that is made possible by a lot of those hydro plants that I talked about just a minute ago. And we do have some natural gas and coal, and although we're exiting the coal. We've got 390 communications facilities, a bunch of microwave, some fiber. Notably, 300 MPLS sites with 260 MPLS sites, over 300 MPLS nodes. We've got some satellite systems. We don't have any TDM or SONET, and we've just cut over to a DMR system on 220 megahertz spectrum. So speaking of more bands, not quite the applicability to this session, but definitely a band. And 700 megahertz upper A block spectrum, we've got a band deployed, which is really what I'm here to talk about. So in 2016, we started a grid modernization effort, which included a fan to communicate with those line devices. We were really replacing a capacitor management system, a VAR management system, not volt management, but just VAR management. It was actually a part of my senior design in college, was to contribute to that system back in 1995. And then when I got hired on at Idaho Power, one of my first projects was actually to put in that system, use one-way communications, which makes it a a real challenge to know did the bank turn on or not. So that system we had, we used it for 20 years. It served us fairly well. It really did save us some dollars in VARs. But it was time to embrace some of the industry pushes of what we now call grid modernization. So we purchased the upper A block spectrum in fall of 2016, and then we went to an RFP process after that to choose both the software for our IVVC system and radio software, or sorry, radio hardware, which John's company was the successful entity that came out of that RFP process. And we piloted that system in the very next year, just at one substation, it was one substation, and kind of tried to work out the kinks the best we could. We started initial fan build out that next year and completed it last year with, as you can see, 360 feeders, 78 substations, lots of load tap changers, voltage regulators, over 1,000 capacitors, and 56 master radio sites, and 1,633 fan radios. So, some of you in the audience may have a larger service territory than us, but we've got enough here to really show some scale. We're not the smallest utility, and we're definitely not the biggest. So our future, currently we're converting reclosers and adding fault locators to this system, and things are going pretty well at this point. And we have some, other possible uses in the future, end-of-line monitors, which we currently today use a lot of cellular for, but, there's areas where we'd like to get those end-of-line monitors where cellular doesn't cover. Especially in Idaho, there's a lot of mountains, we have a lot of canyons, and we have feeders that go up the bottom of the canyons and end at the top of the canyon where we typically don't have coverage. Feeder switches, weather stations, of course, distributed energy resources. The FLISR application, if that goes, that'll put a lot more emphasis on the reliability of any kind of radio system that may be installed, which definitely we have good reliability today, and we'd like to maintain that tomorrow. But how that application really affects this is a little bit yet to be seen. And of course, dynamic line rating. And at the bottom, of course, the more things you add to this system, is there enough bandwidth? Well, that really is the question. So on our fan network, the parameters that we implemented, we did implement a time division multiplex system, which basically allowed us to have a lot more frequencies to choose for frequency planning to avoid self-interference. Of course, that comes with some trade-offs. One of the things that is a trade-off is a half duplex operation, and including transmitter and receiver switching time. Of course, it's actually less than 50% of the time available. Our master stations, we're in some areas very rural, and in other areas we're a little bit more urban, especially in the Boise area. We chose to implement these sites as a single sector, as in an omnidirectional antenna, and that antenna is mounted at 75 to 90 feet above ground, really to get above the foliage of trees. In bandwidths of 50 and 100 kilohertz, we put together a channel system with those two bandwidths and did channel planning. This time with a consultant. We've since kind of brought that channel planning internal, but at the time we used a consultant. This system really yields, between 80 and 320 and 144 and 576 kilobits with adaptive coding, respectively per bandwidth. And the remote radio antennas, this is where the rubber meets the road, is how high can you get that antenna? Can you get above the foliage? And that one's pretty tough. So most of our antennas are about 20 feet. They're not above the foliage. So sometimes that becomes an issue. So here's our current site's busiest loading. This was a graph I took from just, I think it was about 10 days ago. It's showing that the radio side receive data rate in kilobits. You can see it's kind of hovering around 8 kilobits and goes up to nearly 10 here and there, and this is over the course of about 4 months. So you can see it's actually pretty flat, what you would expect. There's not a lot of human activity on this network. It's really just the machine-to-machine communications, which is very predictable. And at the bottom, I've got the notes of the forward channel ACM breakdown and the return channel ACM breakdown, and you can see that this is heavily weighted to the lower end of the spectrum. And that really is a result of trying to cover, a good-sized area with just one master station. So it's less from a capital perspective, but you're going to have some performance impacts of having devices that are further out and devices that don't have an antenna above the foliage, really. I feel that this slide is a little bit more intuitive of how things are going. And this side is really the duty cycle, the received duty cycle of the radio itself, which is reported via SNNP. And over that same time period, you can see that the duty cycle really varies from as low as maybe 7%, as high as as about 40%. And really the average is kind of 30-ish%. That might be not really the average, but that's where the consistent peaks are about 30%. And again, this is really it's not that much bandwidth we're using. You can see here one could say that we're using about 1/3 of the channel, and our bandwidth is only 8 to 10 kilobits. That's really reflective not of the radios, because they're very capable radios, but the fact that a lot of these sites just don't have a great RF path to get back to the master. And I'm sure that John could tell us much more about this, and maybe even some improvements for this. But in general, you can see that we've got some limited bandwidth, which is really why I'm up here talking about this. Is we've got some bandwidth here, but this is not much bandwidth. I mean, it's sufficient for what we're doing, but I mean, it's kind of crazy. Who would want 8 to 10 kilobits of bandwidth, and even to triple that for any new system? That's a really low amount. However, the machines aren't humans. They don't necessarily need all that bandwidth and can operate. But as far as being future friendly, you've got to think about it a little bit. So what could be done to increase the capacity? Change our master sites to dual frequency, frequency division multiplex system, and optionally full duplex. Our channel plan would have to be redone, and it may result in more interference, self-interference really. And that would have some dollars associated with it, but not terribly expensive. We must migrate all the field radios and master stations, and there's where the expense of actually doing this would hit. And then changing to full duplex master radios would have us adding an external duplexer to the master sites to allow for simultaneous transmission. That's estimated to add in about 20% capacity. And we could also move to sectored sites, which would triple the capacity of the system, but it would also be quite a bit of hardware to purchase. And many people, if we were in our position a few years ago, may have gone in with the sectored system to begin with because of anticipated need for more capacity. We chose the single sectored system. Now, I'm not sure if that was the best decision in the end, but it's the decision that we made. Or, in the end, we could do all of the above, and it would cost a fair amount of money, and we feel we could get about 5 times the bandwidth that we have, but that doesn't look very much when you start to compare this with LTE systems. Although in the 700 megahertz, it's a little bit of a challenge for LTE. So currently, we don't foresee a problem with our current use cases. However, that's really a very present-looking view only. It really isn't about the future. We're satisfied with where we're at, but that could change at any minute, especially given those other 2 bullets, that adding private wireless to fleet vehicles. Currently we use some cellular carriers, but some areas they don't cover, and there's some areas we would like to have coverage that we don't, so that kind of pushes in those directions. And of course, bringing back more data on the fan would definitely push the envelope of what we could do with the system. So, a different approach might be the private LTE, but the 700 megahertz upper A block doesn't support full LTE. I think it needs 1.2 megahertz to support full LTE, and this is is that right? 1.4. And so we don't quite have the spectrum to do that. However, due to efforts of people on stage to get this support, is that narrowband IoT band 103 has recently been approved by the 3GPP. And we're glad to see that. We welcome that. We welcome the ecosystem to be larger and more diverse. However, the bandwidth that's available in narrowband IoT is still similar to what we have with 700 megahertz and conventional type radios. So, how much help would it be at 700? Well, I don't know. And that's exactly what we're looking at here is, well, what do we do with this limitation? And of course, it has to deal with other equipment, other technologies, and other spectrum. So I'll turn it over now to Bob.
Great. Thanks, Sean. Thank you, Sean, and thanks. I think it's a great benefit to have an actual utility who's been through the ringer with really more than one frequency, right? So you're now in the process of your digital radio system, programmable radio system on 220, and I assume in part that's greater coverage on the 220 than you would get in other frequency bands because it's a lower, better propagated.
Yes.
So that's, I guess, overall the message here is as companies look to broadband and to go into this next level of capabilities in their networks, what's a good way to accomplish that? Well, one way is to buy the broadband spectrum and find a suitable band that will fit all of your needs. Certainly a valid way to look at it. From our perspective, there's other ways to look at it as well, and we really encourage looking at this dual band approach. I mentioned a little bit, I talked a little bit more about my background. So I previously worked at Nextel and Sprint. In fact, I was responsible for the 900 megahertz spectrum that is now at Anterix, and the 2.5 gigahertz spectrum that is now this yellow layer in the layer cake at T-Mobile. So layer cake is their terminology. AT&T uses something similar, so does Verizon, and Dish is sort of on a similar path as well. So general idea is low band for coverage. At AT&T and Verizon, that's typically 700 megahertz. That's where they deployed their initial LTE systems. Midband, around 2 gigahertz, plus or minus, is where they build their really capacity layer. And so in this scheme, the broad area shown in magenta, according to T-Mobile, is the broad coverage where capacity is generally needed. Cities, points of concentration, they'll go to this yellow band, which is, in their case, it's 2.5 gigahertz spectrum. Much shorter range, much higher capacity. They have, on average, over 100 megahertz of spectrum at that band, so truly a wealth of spectrum. And then in locations perhaps like this one, perhaps like stadiums, other places where very high demand, they actually have millimeter wave spectrum for 5G, hundreds of megahertz of capacity, very short range, doesn't go through pretty much anything, but can provide a massive capacity in these places where it's needed. And so, everybody at the Super Bowl can not only be at the Super Bowl, they can be streaming themselves watching the Super Bowl. I don't know what all is done with this, but massive quantities. In the case of critical infrastructure, electric utilities, other utilities, the ultra high capacity millimeter wave, so far that's not needed. I don't foresee it as being required. And so really it becomes, in that case, a dual frequency network. And I can assure you that these carriers who spend billions of dollars a year looking at this, I was formerly part of this large organizations looking at how to optimize. They look at the numbers, right? They figure out what the best way is to accomplish this combination of coverage and capacity. So, based on that wisdom, we're recommending something we call dual unified efficient transmission, which happens to come out to be DUET in the acronym. And it really means this concept of low band for broad coverage and a higher band for capacity where you need it, with the expectation that you're not going to need that higher capacity everywhere. Now, if you do, this might not be the right answer, but ask yourselves where you need it, and it also gives a way to get there, right? Is either start with a broadband, build where you really need it, and come back and put the coverage layer in later, or maybe a more logical approach is start with the lower frequencies spectrum, get the broad coverage, and then as you have demand hotspots, fill it in with the higher frequencies. So that's the overall recommendation that we encourage folks to look at. So I'm going to talk. John's going to talk, I think, really about why that makes sense and some of the technology trade-offs and advantages and disadvantages. I'm just going to talk about the spectrum bands that I think are most relevant in this. It's not entirely a coincidence, but it's mostly a coincidence that we represent holders of all but one of the bands I'm going to talk about. If there's another band during the Q&A or John can cover, certainly be glad to cover that as well. We start with the one example of a low band spectrum that could make sense. Generally low versus mid. Most people make that dividing line at 1 gigahertz. It's kind of a matter of convenience, but it seems to fit with what's actually happening in the world. So we've been representing one of the 700 megahertz license holders for years and years. Many of you have probably heard me talk about this, or John Wisłowski from Access Spectrum talk about this. It is being widely used. About a third of the country now has been licensed to critical infrastructure. Many of those systems, most of those systems have been built out. Some have not yet been built out. It has not been built out with 4G, 5G systems because Band 103 was approved about 60 days ago by 3GPP. So this is brand new approval. It's been built out with industrial radios from companies like 4RF, and I see Max in the audience, and GE, and I'm sure there's others. And it's providing these field area networks that meet the most critical needs of electric utilities and other critical infrastructure companies. Very high power capabilities, excellent propagation. It is officially designated as 4G, 5G band, but that equipment is mostly unavailable. You can get it from a company called Pololi, cable free, and I think we're going to get an announcement soon from Ubic. We'll see. So there are 3GPP solutions that are in the band, but they're not from the big names so far. So we'll see how that comes along. Those are really the highlights of those bands. Good news is it still remains available in about 2/3 of the country. So we encourage everybody to take a look at this. Be glad to talk to you about it. All right, the band that we don't represent, I'll try and do a good job here. We'll certainly open for comments or questions at the end. Is the 900 megahertz Anterix band has been the company that has acquired these narrowband licenses. Today, the broadband plan I'm showing is the future band plan. In most cases, it's actually been approved in, I think, 21 counties so far. There's another 160 some that are on file with the FCC. So they got a long ways to go before they get to this band plan in most of the country, but they have accomplished this. And that process is relocating existing users to the lower end of the band and then having a 3x3 4G capable band 8 modified. It's a different spacing than they have in other parts of the world for the duplex spacing. And it's now been adopted by 3 utilities. So they've had some significant success here in the last, I think, 4 years that they've really been marketing it into the utility space. Good power, excellent propagation, developing ecosystem, and I think we're going to see this in most of these bands. And I'm sure you have a chance to speak with the folks from Anterix. They can tell you more about it. I would say concern is this question of how long will it take to actually get the band clear in your area, and do you want a path to 5G? So this is at 3 megahertz wide. The 5G standards were developed. They're a minimum of 5 megahertz wide channels. This does not have that capability. You are, on the 4G path and with questions about evolving to 5G. All right, so really those are the two examples that I think are most relevant in the low band. In terms of the mid-band, we have three different examples. First one I'm going to talk about is something that's brand new on the market for utilities. It's been going through the regulatory process for some time. This is the so-called L-band from a company called Legato. We are representing them. It's nationwide spectrum. It comes from the satellite services world. And I mentioned the regulatory concerns. There was a concern that because the GPS is in the middle between the uplink and the downlink, there could be interference. In order to get that through the FCC, Legato, long series of negotiations, they agreed to an offset in terms of the spacing and to minimize the power. So the power levels on this are significantly lower than what you will get with most terrestrial broadband frequencies because of this concern about interference with GPS. But with that change, they've gotten 3GPP approval, FCC full approval, unanimous approval. This spectrum is ready to go. There's equipment available soon, meaning this quarter from Mavenir, next quarter from Nokia. So, the ecosystem is starting to develop. This is band 24, or for 5G and 24, and it's, significant new news. Total 30 megahertz, by the way, right? 20 on the uplink and 10 on the downlink. So, lots of capacity, and the possibility of actually delivering not just monitoring and control services, but actually the services that would allow you to deliver broadband to customers in a rural environment. So perhaps more relevant to most utility applications because of the higher power involved is that, I love the name of this band, 1670 to 1675. It's going to be easier when we can call it band 10X, but 3GPP has not approved it yet. This is full power, in fact 2,000 watts downlink power. They have more in some places, 4 watts on the uplink. Being in this low mid-band space, both the band 24 and the 1670 to 1675 are going to have good propagation. This is a very interesting combination as a mid-band capacity band along with something in the lower frequencies. And I encourage you to take a serious look at this one. We're actively seeking parties that will do trials and demonstrations. We're working with all the manufacturers to develop the ecosystem. This is an exciting one. We expect 3GPP approval for this band later on this year. They've already been through the band L-band, band 24, and so they have the experience that it'll take to get through. All right, and the last band, I think probably everybody has heard a lot about CBRS. Lots of equipment available, relatively cost-effective, right? So cost-effective on the GAA tier, you don't have to pay for the spectrum. You do have to pay for the SAS. That can be a significant expense as well. There's also, in many locations, primary access licenses available, which gives you exclusive use to that spectrum, subject to the tiering, but in much of the country, it's really truly exclusive use of the spectrum. You still need the SAS capability. We are representing a number of sellers in this band. One of the things I think we're going to see, particularly in this band, we may see it in some of the other mid-bands, is partitioning. So if you only want to cover your substation, you could do it with this, right? You could get a PAL, just cover the substation. Who the heck else is going to want to be in that substation? You'd have those full rights. That could be a very effective kind of an approach. And it's also expected for convention centers and stadiums and that kind of thing. But this has a lot of capabilities in terms of this concept of broad coverage at some lower frequency and then really very spot coverage. Obviously at 3.5 gigahertz, this is going to have, and low power, relatively low power limits, this is going to have much shorter propagation, but still could be very effective in hitting those high demand areas. So this is an excellent one, I think, to consider for a duet type of application. So I tried to summarize this in kind of what's good and what's to be concerned about across these different bands. By the way, I mentioned another band that would look pretty green on most of this is 600 megahertz. The challenge at 600 is that really it's a carrier band, except in maybe 20% of the counties around the country. It's basically tied up by parties that are not going to part with it. So excellent if you can get it, but in most cases you can't. So you see even more green, I think, with 600. But this kind of goes through the different areas. Given the time situation, I'm not going to try and go through this. But basically, and you'll have access to these slides, this is a chance to say, well, what's important? If throughput is important to you, maximum throughput, then 700 doesn't look so good, and some of the higher frequencies look better. If ecosystem is an issue, you're going to want to take a look carefully at that. But there are some significant capabilities here and immediate availability, right? So good news about spectrum, it hasn't always been immediately available to this. For broadband spectrum in particular, this industry has not had immediate access. Now you have choices, competition, immediate access. That's good news and really should help people plan their futures. So with that, I'm going to click to my last slide, which is just kind of Q&A. We'll do that at the end. John, you're up.
Thank you. Okay, well, good morning, everyone. I'm the last of the three speakers for this session. My name is John Yaldwin. I'm the CTO at 4RF, and it's my pleasure to pick up on some of the points that have been made by the earlier speakers, and perhaps give you a bit of a view, taking Bob's duet idea and expanding just a little bit further. But before we talk about some of the specifics, I want to make a bit of an introduction about why people are looking for private 4G and eventually 5G networks. Right now, private traditional narrowband radio systems are where it's at, and state of the art is 256 QAM, 500 kilobits per second, and dense networks with up to 10,000 remote terminals. So that's what we see today. LTE and cellular, of course, have had a role to play for some time. There have been a lot of offerings from public carriers to try and hook utilities into their networks, but all of those public networks have suffered from particularly latency issues and variable capacity. When school gets out, you've got all the school kids today using their phones, and that can really drive capacity out of the network during a period of half an hour to an hour, and if you happen to have a utility event during that time, you can be in trouble. Now, carriers are trying to step up to address that, but private LTE is the ultimate solution. So there are a lot of new opportunities now for private LTE, but they've only become real because of spectrum availability, as Bob's touched on. I won't enumerate the bits of spectrum that are available, but I will talk a little bit about their characteristics in a couple of slides. So as we work towards private LTE, there are some important considerations. We have the choice of public LTE, and carriers like AT&T, for example, and Verizon with their FirstNet and Frontline programs are trying to offer services to utilities that take away some of these latency and variable capacity concerns. So it certainly remains an option for an LTE network. In terms of private spectrum, we now have capacity available through the CBRS initiative from the FCC and private initiatives such as Ligado and Interix, and indeed 600 megahertz as well. We need to consider the use cases, resilience improvements. We need to talk about replacement for 3G with AT&T retiring their 3G network and others, whether the system's going to be greenfield. If we have the luxury of a greenfield system, that's superb. We'll be able to offer quite a uniform approach if private LTE is within the budget. And we've got from COVID the sudden increase in workforce mobility requirements, capacity that's needed to enhance the field force, allow them to work effectively in the field. So these are some of the drivers that are pushing us towards private LTE. But there's one thing that is important, and that's there's not one solution that necessarily fits all. And I've taken here some examples from the utility area where the different DA type applications from, say, sectionalizers or cat banks, those requirements will be different from, say, metering aggregation, transformer monitoring or workforce enhancements. So you need to look carefully at the various use cases to decide which technology is going to be appropriate. And on the subject of technology, we've seen a tremendous growth in the technical capability of cellular networks, ranging from 3G 15 years ago right through to 4G enhanced LTE and now 5G, offering a superb range of capacities. And that is, I guess, it's an advantage of cellular technology, but it's also a disadvantage that we have these regular updates in technology. But the good news is that LTE and 5G share many of the basic control underpinnings, so I expect LTE and 5G to remain dominant technologies for a much longer period of time than perhaps was the case with 3G. When we look at industrial IoT and how this might be done with LTE, there are some important considerations. And one is that the original cellular designs were very asymmetric. They were very downlink centric. It was all about delivering videos to phones rather than bringing capacity back from the field. And so the download rates were considerably higher than the upload rates, and that remains the case still today. However, development, for example, in uplink carrier aggregation has seen uplink carrier capacity improve dramatically. And that's important when you're trying to overlay things like video on top of other control system designs in the field area network, because video is very much an uplink thing. You're not going to download video to the field. You've been uploading video that's monitoring switch yards and things like that. These are important design considerations. But before we can really talk about private LTE, we need to think about spectrum. We can't build private LTE networks without spectrum, but all spectrum is not the same. It looks attractive, CBRS, potentially free access, 600 megahertz, quite expensive. Why is that the case? Isn't one block of 10 megahertz the same as another block of 10 megahertz? And that's not really what we need to think about. It's not the bandwidth, it's kind of where it's at that's important. And utility networks face constraints. There's obviously the budgetary constraint, but on the other hand, put a flash news system and you'll find more and more applications that need to be loaded onto that network to make the system go. So one axiom I can say from the beginning, from our pretty long experience of involvement with utilities, is that often what you supply today, people will say great, and then they'll add all sorts of applications on until capacity is exhausted and they want to know what's new. So that business of monitoring capacity and building for the future is a really important theme for either a private radio system or for an LTE system. So let's talk a little about the spectrum itself, because I think that is quite important. To build a radio system that you're going to own and operate yourself, you can get FCC licenses, and those are typically done on a channel-by-channel basis. But there are no FCC apparatus licenses that you can get that will allow you to deploy LTE. You need to go and buy a chunk of spectrum that you can use within your area exclusively for LTE or for private radio. And looking at the system, the bandwidth that's available at the left-hand side of the slide is 50 megahertz. Then we have VHF, which is great for very low capacity systems. 220 in use for land mobile radio in the case of Idaho Power, but in rural Texas, for example, 220 is quite heavily used for private radio systems for SCADA. We have the 450 megahertz band, typically available on a channel-by-channel basis, but there's a limited amount of private spectrum there available that were, for example, paging systems. You can aggregate that spectrum and get 50 kilohertz, something like that, for 450 megs, so useful. 600 megahertz, as Bob said, it's prime LTE real estate. And the golden rule is any spectrum that can support 4G and 5G and is already a 3GPP approved band, the carriers will be all over it. There has to be something wrong with the spectrum to prevent AT&T and others signing up to buy it, or lining up to sign up to buy it. 700 megahertz, we've got two 1 megahertz wide bands, very popular for private radio systems, not wide enough for traditional LTE. Okay, you can fit narrowband IoT, but you need to look at the capacity that you get from a private radio system versus narrowband IoT before making a decision on that. Anterix 900, and of course there are MAS licenses that are available direct from the FCC in that spectrum. So yeah, that's doable. Ligado, very powerful offering. I'm very enthused by the Ligado availability. There are 3 chunks of spectrum there. 2 will be very attractive to commercial carriers, but there is 1 chunk of TDD spectrum, great bandwidth, 10 megs, that I think would be ideal for utility use. And if you're a utility, I would really recommend that you try and lock in a deal on that before the price gets too high. And the price will be driven by the availability of the subscriber ecosystem. At present, that's a bit limited, so the price might be a bit softer. When the ecosystem for the subscriber equipment becomes solid, I expect the price will probably go up. Bob probably doesn't want to know that, but I think that'll be what will happen in my view. And then finally we have CBRS, which is superficially attractive but comes with some disadvantages. Now, to talk about those advantages and disadvantages, I want to introduce onto this slide some of the other users of the spectrum, because the radio spectrum does not exist in isolation. So what I've shown there in blue on the left is the FM radio band that you tune in on your car radio. I've included the military band, 225 to 400, between the 220 and the 450 bands. I've included a nav band around 1 gigahertz where we have primary surveillance and secondary surveillance radars and other military and civilian aeronautical systems. There's GPS in there as well. We have the ISM band at 900 megahertz. We've got the Wi-Fi ISM band at 2.4 gigahertz. And as you probably know already, the distance that your FM radio will receive over and the distance that your Wi-Fi will receive over is quite different. Now obviously the FM band, the transmitters are running kilowatts, and your Wi-Fi ISM, you're only running hundreds of milliwatts. But you know, that's not the only consideration. The frequency, the wavelength of the bands matters. And you know, as a general rule, the low end, the lower the frequency, the longer the range, but the lower capacity. And at the high end, the higher the frequency, the shorter the range. And you know, typical ranges for CBRS, you know, is about a mile. Don't expect that you're going to get 10, 15 mile coverage from CBRS. It just can't be done. Now, when you look at trying to build platforms that integrate these various things, what can we do? You don't want to bet the whole farm necessarily on one solution. Maybe in the future, private LTE will be mature enough to do that. But right now, we're seeing customers that have a mixture of different platforms brought together. There'll be private LTE, there'll be public LTE, and there'll be private radio. These networks are brought into the central office through these various clouds. And that's the kind of theme I want to riff on for the next couple of slides. Let's start off with private radio. It's obviously an area that 4RF has been in for a long time. And I want to talk a little bit about 700 megahertz. So 700 meg, state of the art, it's 256 QAM, it's 3 sector antennas, it's data rates of about 500 kilobits per second. There's a very vibrant ecosystem of vendors in this band. Some mainstream, some not so mainstream. For example, if you take 2 of the major vendors, GE and 4RF, you can swap a sub-network from one vendor to the other and get essentially the same functionality. So that is kind of the main ecosystem advantage there. It really is quite powerful. There are something like 25 utility deployments in this band. Very small advertisement for 4RF, we have half of those. I'll just give you a bit of an idea of what's possible. It's a very popular band, and as Idaho has recognised and other utilities have recognised, it's a band that offers a great deal of control over your destiny. But there are the capacity limits. If you need more than 500 kilobits per second, you need to start looking at private LTE. Now on private LTE, what can we do with the band? Well, we can roll out our entire network deployment in that band, or we can share, and this might be the best approach as you migrate towards private LTE, a private radio network and a private LTE network, and using the various characteristics of those to support each other. The private network might be driven by deterministic requirements and latency requirements. The private LTE network be driven by, say, capacity requirements. And then to summarize, I want to look briefly at these various technologies and how they stack up with each other. So if we start off with VHF, UHF radio, you can do that in FCC licensed spectrum, or you can do it in private spectrum. Provides reasonable speeds. It's not what we're used to with LTE, but for private radio systems, control systems, monitoring systems, data rate to 500 kilobits per second, that will cover a lot of the requirements. Latency is good. It's not as low as can be achieved, say, with a microwave system, but it's exactly the right kind of latency for control applications. And the best part about it, it's deterministic. It's not going to vary depending on, say, subscriber loading, which you'd have in a public LTE network by contrast. High priority, relatively low system cost. It's low cost to get into. Terminal cost is reasonable, not as low as perhaps LTE with the very cheapest devices, but when you compare the security that's gained and do a comparable comparison in terms of, say, protection from transients and those sorts of things, the terminal cost between LTE and private radio is pretty much a wash. Security is really good depending on the vendor, power level's great, reliability good, etc., etc. So there's a lot of green points there for VHF, UHF radio. Now in comparison, unlicensed radio, the experience is very variable, and that comes down to the nature of unlicensed radio. You're sharing the spectrum with other people. What works today may not work tomorrow if someone else becomes a large user of that spectrum. So there's lots of white blocks in here, which means it can be good or maybe not so good depending on your circumstances, but there are some real disadvantages. In particular, the lack of reliability, the fact that someone else can deploy a system and blow your system out of the water. So that's something to be a bit aware of. Unlicensed has its role, but you need to be careful. Public LTE, generally good. If you want to consider carving out a private system within a public LTE infrastructure, which is possible with some carriers, then you're looking at a very high OPEX component. Which is a bit of a red. The power level for the terminals is of course limited because it's cellular, and then the other characteristics, latency, priority, etc., they're all a bit variable because it'll depend on the deal that you achieve with the carrier. But what you have to remember is that you might think that your 40,000 or 50,000 terminals is going to be a big deal to AT&T. Well, guess what? It's not. They don't care about your 10,000 terminals. They've got 5 million or 10 million subscribers that they need to worry about. Your priority is very low, and you're expecting a great deal for the SIM card cost. Well, they'd much rather have the home user and upsell them to 3 lines at $90 a month. They don't really care about you trying to do a deal in there. Believe me, it's not a big area for them. Now, private LTE then addresses some of those shortcomings. Sure, we do have the issue of buying the spectrum, that is a cost, but a lot of the variables from the public LTE turn into solid greens when we talk about private LTE. So there are some real advantages in private LTE systems, and for a capacity play, it's definitely state-of-the-art and where things are at. Now, narrowband IoT is kind of a play on the private or indeed public LTE. We're talking about lower data rates, we're talking about more specialized terminals. But there are quite a few advantages in narrowband IoT, but there are some not so obvious disadvantages that are really important to factor when you look at some of those use cases we talked about before. So, I try and be fair when we look at these technologies because, each of the vendors of these different types of technologies, each of the proponents of these types of technologies will obviously accentuate the positive and try and minimize the negative. But when you are looking at a new system, you need to look at where am I spending my money, what are my use cases, and what is the technology and what do I want it to do before making a decision about these various offerings. And I want to just touch on one thing. Up until now, there's been a lot of talk about security, and each vendor says, yes, my system's secure, but you've got no real way of knowing whether those systems are secure or not. You've only got the vendor's word for it. Well, through the magic of taxpayer dollars, we now have this FirstNet program. It's a NIST initiative, and it's administered by AT&T. Now, even if you're not going to be an AT&T FirstNet subscriber, even if you never plan to take on that service, a LTE device that's been through the FirstNet program has been independently audited, and I mean literally taking the source code for the router and running it through the mill to see what's in it. This work has been done. So when you're looking at LTE devices for a public or private network and you're a utility, you owe it to yourself only to look at vendors that have FirstNet certified products. So with that little bit of an advertisement, and I don't work for AT&T and I don't play an ATE salesman on a TV program, but I do want you to be secure, so bear that in mind, please. So thank you very much indeed for the opportunity to talk to you, and I guess we've got a few minutes for questions, so I'll pass it over to the whole panel.